There we go. Okay, so today I'm going to go over what new capabilities there are in the thermal analysis space for FFlex. Brand had touched on it a little bit. I'll do a bit of a deeper dive and talk about the individual functionalities that we have. I'll go over some slides with applications, and then I'll jump into a live demo to kind of show you interactively where all of the buttons are and things like that. Okay, so to start off with, we now have the thermal loads are an option within FFlex. So what you can do is apply boundary conditions, thermal boundary conditions, to a FFlex body, and then that conduction will transmit through the material, and you end up with thermal strains that occur because of that. And we'll kind of look at some graphical representations of that. But basically what happens is you'll see the material begin to expand or contract based on the conduction happening within the material. So some of this is a bit of a repeat. To kind of go back to what we had in V9R3, the thermal load was added. So you could apply a fixed temperature to materials based on a given element having a set temperature, and you could have that as a static or a transient behavior. In V9R4, you actually apply just the boundary conditions. So for example, a thermal input, so a certain number of watts coming into a surface, for example, or convection bringing heat away, and then that temperature is going to travel through the material, and you'll be able to have a much more accurate representation of what's happening to the material over time. And then the last point, so there's 4 different types of thermal boundary conditions, and I'll go through each of them in more detail. But it's the an actual wall temperature, so you can specify a given temperature for a set of elements. You can apply a thermal flux. You can apply convection, bringing heat away from a system, and then internal heat generation. So these are the actual boundary conditions and the types of objects you can apply them to. So first off, the wall temperature. So you directly specify temperatures at a node over time, right? And then there's an actual heat flux. So this is going to be applied to a patch set, and this is what I'm going to show in the kind of interactive demo portion. And this will, be watts per meter squared, or millimeters squared, whatever units you've selected, right? And then there's also convection. So you'll be able to either add or remove heat to a patch set based on a convection coefficient. And then finally, heat generation. So this is going to be internal to an object. So you'll apply this to an element set. And if you have like a chemical reaction happening inside of a material, the best example I could think of was concrete. It's an exothermic reaction as it cools down. Obviously, that's not something that you would model using RecurDyn, but that kind of effect where you have a chemical reaction adding or removing heat from a material. And as a part of this, you need to define additional material properties, right? So, along with like Young's modulus and density, you'll be able to specify thermal coefficients, a thermal reference temperature, so the starting temperature, the undeformed temperature of the material, and the specific heat, as well as the thermal conductivity. And then these are the material types that you can apply these boundary conditions to. So you'll have beam elements, shell elements, and solid elements. But it's only valid for isotropic materials. So that's something that you have to keep in mind. And lastly, as part of this enhancement, there's another tool to kind of complement it, and that's the RTL file generation. So the RTL file was the input file that you would use in the V9R3 thermal load, and this just specifies a node temperature over time, or it could be steady if it's constant throughout the simulation. So you'd have to prepare that by hand previously. as part of the new thermal solver, you can run the simulation and then output either a snapshot in time or the RTL file over the length of the simulation. And this allows you to run a thermal simulation and then output this data in a plain text format, either for post-processing or if you want to use the thermal load capability that is still there. If you have workflows defined with that, then you could continue to use kind of both of them to complement each other. And for post-processing, just like all the other FFlex outputs, you'll be able to generate contours of the thermal field as well as thermal strain, in each direction. So to go through a couple of examples of areas where you might want to use this, this is probably the quintessential textbook example, bimetallic strip. So this is, old thermometers before we had digital sensors. This is what they would use. And it's basically two bonded materials, and they have different thermal expansion coefficients. So as they heat evenly, one is going to expand more than the other, and you end up with this deflection. So this is the kind of thing that you would be able to model in RecurDyn now. And this is similar in concept to what I'm going to be covering in the live demo, where instead of having two materials, we're just going to have one material, but there's going to be a thermal gradient. So one end is going to expand more than the other. So going through the this example kind of set up in RecurDyn, we have, where's my mouse? We have these two materials, so you can see red and blue, and we're defining, different material properties for each one, and then assigning boundary conditions to each of them. So we have a wall temperature on either side, and this is going to be an expression for temperature, so we can, make that a function of time. Oops. So in this case, we have a step function to kind of smoothly bring us up to temperature or down to temperature, for example, and then we'll see what happens to that material over time. So and then this is the end result of that that behavior. So one of these materials is going to expand or contract more because of its thermal coefficient. And then very similar example. So this is, again, old thermometers used to use this. You have a coil that is going to expand or contract in reaction to changes in temperature, and then that's going to spin this dial here, so you could get visual feedback to what's happening in the room, right? And what we can do in RecurDyn is apply a heat generation at one end, and then that's going to move heat through the system and then cause the spring to either expand or contract and then move the needle over here on the left. So we can see an animation of what that looks like. Okay, so I think the next thing I'm going to jump into RecurDyn and kind of show you a toy example that I put together. It's a little bit of fun. So let me. So we have is a model of Hubble. Actually, it turns out NASA puts out 3D printable models of certain telescopes. So I was able to pull that into RecurDyn and then assign some equivalent material properties to the body. But this gives us some kind of interesting visuals while we're looking at the model. So and then I took out the solar panels and the boom and replaced those with flexible bodies. So we have these 4 solar panels and this, so these are all, I think, solid 8 or solid 6 elements. And then a beam element representing this boom. So this is on either side. And then those are rigidly connected or fixed to the actual telescope body. And we have, I can zoom in to kind of show what's going on here. So we have fixed connections between these nodes here at the edge and then the beam element here. So these are rigidly connected. And what happens is we have conduction happening, a thermal input on either side of these panels, and it's only applying to one side, right? So basically, solar energy is coming in and it's heating up the material. And what happens with very large spacecraft now, and it's becoming kind of more of an issue as we build larger and larger structures in space, is we end up with like these thermal shock events. So one side of the spacecraft is going to be illuminated while the other is still in shadow. And then, so this side is going to start to heat up, and then maybe a few seconds later, this side will start to heat up. And with very large and flexible solar panels, you end up with that kind of bimetallic effect, even though it's only one material. One side is hotter than the other for some period of time, and if the stiffnesses of the system are wrong, then you can end up with this begin to flex and then induce vibrations in the system. And very large spacecraft are very flexible. You can't afford to send a bunch of steel up, so we end up with these very large flexible structures in space. And what I've done is set up the materials such that we have a kind of exaggerated effect. So I'm going to start to play this now, and you'll see one side begin to bend. So this is basically the first side that's been illuminated, and then this side 2 seconds later starts to get illuminated as well. And we can end up with vibrations being induced into the system. So I can kind of play this back, zoomed in on one end over here. And we see, so this begins to deform, and then conservation of angular momentum says that the other side needs to move as well, right? So this boom begins to flex. And, this could cause problems with pointing and things like that. In the case of Hubble, if we're looking at things very far away, we need high degrees of pointing accuracy. So very small, subtle changes can cause large problems when you're taking an exposure for a month or something like that, right? So I'll kind of reset this and then walk through the actual setup. The actual setup process for adding this into a model is pretty straightforward, but it allows you to do, some pretty interesting types of analysis. So like I had already mentioned, these are just two subsystems with the flexible bodies. And inside of all of those solar panels, I've defined material properties. So there's, a reference temperature and thermal expansion coefficients, et cetera. But I'll kind of walk through the mechanics of adding the, a heat flux in this case to the system. So we have these 4 forces, and if I go into one of these, it's going to highlight the patch set that's associated on each of these panels. And it's on my other screen. Okay. So in the actual setup process, all we have to define is the patch set that we're applying a thermal load into, and then the direction, right? So am I adding a thermal load to the system, or am I removing heat, right? And it'll preview the direction for me. So if I kind of zoom in here, we can see right now we're putting heat in, right? And then for the actual heat flux, we have an expression defined, so I can go into this. And in this system, I have 2 expressions defined, one for an instant radiation load from the sun, and then a delayed radiation. So this is just a step function that at 1.5 seconds begins to add heat, and then at 2 seconds, it's, quote unquote, fully illuminated. Go in here. And the process for adding any other boundary condition is really the same, right? So I could go and apply a temperature, and instead of applying it to a patch set, I'm going to be applying it to a node set. So in this case, I have node sets for this connection here, and I could apply, a set temperature or an expression that defines my temperature. Maybe it's changing over time. And exactly the same process for adding a convection coefficient. I would apply this to a patch set, and then specify a heat coefficient and the ambient air temperature. And same thing for heat generation. If I wanted to export out the RTL file, I can just go here and then say on this node set, I want to know what the temperatures look like for each node, either at a set point in time. So I could say at this time step, I want to know what the temperature was, or I could do a transient and I'll get data for all of them. And then I would just specify, the output name, and it would give me a plain text file, so I could post-process that, maybe in Excel or MATLAB, or I could use that in subsequent simulations using the thermal load up here. And then the last thing I will show is the contours. So this is going to behave, the same as any other, if you were looking at displacement or stress. What I'm going to do is go to temperature. I will show this. I'm going to apply, and then I can play back and see what the temperature looks like over time. And we can very clearly see that this side begins to get heated first, and then this one is heated a few seconds later. And there's a thermal gradient happening through the material, and that's why we're getting this deformed behavior. Okay, so I think that covers just about everything that I wanted to go over on the thermal side of it. Like I said, pretty straightforward to add into a system, but it allows you to do new types of analysis and answer new questions.
Okay.
Do we have any questions in the chat?
Yeah, I'm not
Grant,
seeing
they really
any.
do, they hide the chat window when you're presenting, huh?
Yeah,